Welcome back, everyone. Next up will be Christoph with the talk about SQLreduce, minimizing SQL queries, especially recursive ones, I guess. Maybe.
Possibly, yeah. Yeah, hello, everyone. Today I'm talking about a tool which I was developing earlier this week for the company I'm working for, Creditive, which has been acquired by Instacluster last year, which has been acquired by NetApp last week, so everything is in flux at the moment. It's not related to Debian at all. It's a Postgres development topic, but I thought it might be interesting to show a bit of nifty things that you can do when doing quality assurance on software. So the whole thing is about bugs, mostly in the Postgres database server. SQL is a complex language, as we've already learned in an earlier talk today, and some queries actually trigger bugs in the Postgres server. Of course, there's an extensive test suite that Postgres is running, but no test suite can cover everything, and sometimes Postgres even crashes. And to find bugs in that area, a colleague of mine has written a tool called SQLsmith, which basically generates random SQL queries, runs them against the server to see if it can trigger any bugs in there. There's a similar tool called csmith, which can generate random C programs to trigger compiler errors, but we are now looking at the SQL side here. Just to give an idea of what SQLsmith is doing, we have a database running here, so we can just say, I think I have the command line already here. We can just say we want to run SQLsmith against the database server running on that machine. It will connect to the database, look around which data types do exist, which tables do exist, and then it will start firing queries at the database. The E means it did trigger some error, but many of those are also just errors in the query, like it was using an invalid database data type or something. So what we are looking for is any error message in that list that is kind of unusual. To see how the queries are looking, we can just check the server log there, and just randomly stopping anywhere, we can see that the queries generated there are sometimes really, really large. Okay. So, this is where the actual talk is starting. So, let's pretend it's April 2018 and SQLsmith has found a query that actually makes the server crash. So, this is the query that if you run it against the database server from that time, it will actually trigger a seg fault. We can actually do that. The query is here in a file. Oh, it's still running. It's in that media directory. So this is the query that was actually making the database server crash. To check, we can just connect there. It's a temporary server, that's why the connection string is a bit longer than usual. So if we run that query against a database server running on a certain Git commit from back then, it will just disconnect and say the server has crashed. And if you look into the log, it says something like, if we have to look at more context. So it would say the database server was crashing and the failed process was running this query. Okay, so to actually make this useful, well, the query back then was reported to Postgres upstream. Someone was, the question is, which part of that query is actually the part that is triggering the SEC fault. It's not the whole query, it's just one bit or combinations of bits in there that triggers the actual problem. The question is, can we actually get at what the problem is? So far, this has been manual work, and back then, Andrew Dunstan, one of the Postgres developers, was having a look at the query and reduced it to this one, which is much shorter than the original, but it's still very, very complex. But the good news is we can actually automate that process, and if we do that automatically, we can figure out that the crashing query is just this one. So just for a bit more of context, the queries are all running against the Postgres regression test database. So you can't just run this on an empty database and it will crash. You have to execute the regression tests of Postgres before. It will leave some tables behind, and when running this query on the tables left behind by the test suite, you will get that crash. So, yeah, how does this work? This is what this SQLreduce tool does. It's basically the opposite of SQL Smith, which generates query. This one cuts the queries down again. The tool is based on a library called pglast, which is a Python module that exposes the Postgres parser in Python. And that module itself is based on libpgquery, which is the C library which drives the whole thing. libpgquery is actually inside Debian in Unstable. pglast is unfortunately not yet in Debian because libpgquery requires Postgres 13, and we are already on 14 in Unstable, so I haven't uploaded that one yet. And of course, pglast and SQLreduce will be uploaded as soon as there's a compatible Postgres version that works. But you can get it from the apt PostgreSQL repository I'm running. So what SQLreduce basically does is it takes the input query and translates it to a parse tree. Then it enters a loop. It replaces the parse tree by a more simple parse tree, translates that parse tree back to a query, runs that query with a Postgres server, and just compares the error message it got with the original. And if the reduction was successful, it will continue with this more simple parse tree, and if not, it will try other simplifications. So yeah, all that we have to define now is what does more simple actually mean. And in this case, it's quite simple. I just produce a parse tree that has less elements. So we just take a parse tree and start removing elements and see if the result is still breaking in the way we want it to. So yeah, what we can do is just to run, take some query, either on the command line or from some file, and feed it to SQLreduce, which will just run it against the database. So we have an actual demo here. What we can do is we just say SQLreduce. We connect to exactly the same database as before with the same input file there. And if we start that, it will say the query makes the server crash, server closed connection unexpectedly. And as you can see, as it's going on, the queries it tries is always getting a bit shorter. And in some cases, it has reduced the query so much that there's no error anymore. But on the way there, there's different, it just gets there by slowly removing elements from that parse tree. Yeah, and in the end, we have this minimized query. So this is the shortest query it could find that would still make the server segfault. It took about 14 seconds to get there. The tool is much faster. It's just that slow because Postgres is doing crash recovery all the time after it has crashed. So if you are debugging a non-crashing query, it will be much faster. Okay, yeah. To demonstrate or to illustrate how it actually does it, we use a more simple query that we want to reduce. The query is slightly nonsensical, but it works for the job of demonstrating what we're doing here. So we are selecting pgdatabase.rel tuples divided by 1000 from pgdatabase and pgclass, which are Postgres internal system catalogs, were some condition order by something descending, and so on. So taking the statement, converting it to a parse tree, it will look like this. So we have a select statement. It might be a recursive query, but then the parse tree is more complicated. And we will use this to reduce this to a more minimal example. More minimal in the sense that the query is actually faulty, namely this column pgdatabase.rel tuples does not exist. So there's an error in there, and we want to spot where it actually is. Okay, in this short example, we could just read the query just to demonstrate what the point here is. So the first thing we can do is we have a query here, and it says limit 10. So maybe we can try to remove that. So in the first step, we run the query without the limit 10 at the end. And yeah, the error we are getting is still the same one as before. Then, the next step would be we have an order by here. We can try to remove that. Yeah, and if we remove that, it will still result in the same error message. Now, the tool tries to remove the entire the target list of that query. We say select something from something, but we can actually try not selecting something. And surprisingly, the error message is still the same because it was saying pgdatabase.rel tuples twice in here. So this here is just enough to trigger the problem. Now, the first non-successful reduction step happens, namely the entire from list is removed. We try this, select where something, but now the error message is different. It's still talking about pgdatabase rel tuples, but in this case, the error message is not missing column, but missing from clause entry for some table. Okay, so we have to go back to the step before and look at something else. So we are back at this query, and now we try select from pgdatabase, pgclass without any where clause. This is the first time we have a query that does not error out at all, but we are not interested in that. We are looking for something that generates that error, so this is a dead end as well. So we are back at the previous query. At that point, the parse tree looks like this. So far we've just removed entire subtrees. And now we have to do something more complicated. We have to descend into the tree and try to remove elements in there. So the first thing it does is to walk into the from clause. So at the moment we have from PG database and PG class, but we can try remove elements from that list. So let's remove PG database. We are left with the query select from PG class where something. That doesn't work because we need the PG database table for that error message. So we put that back, remove PG class, and we are at select from PG database where something. That worked. And now the tool will descend into this where clause. We already figured out we cannot really remove it, so we have to walk into it. We are simplifying this one here. And now what happens is that expressions are pulled up. So it says where 0 less than something. We could try to run this one here, where 0, which is not legal SQL because it's not a Boolean, and of course the error message says that, but we can try. So let's walk into the other branch, where PG database rel tuples divided by 1000. Yes, that worked. And we can again walk into this expression and pull up the PG database rel tuples thing at that point. And at this point we have actually reached the most minimal query that will actually raise this precise error message. So yeah, that's the path tree we are ending up, and the query at the end. Okay, so there are several rules which are applied to simplify the path tree. We've seen most of them already in the examples. Not going too much into the details here, but it's usually just, it doesn't do anything fancy, it just shuffles path trees around. So, of course, there's some things that SQLreduce does not do yet. Here's another query that was found by SQL Smith, I think, also around that time back then. Select something over partitioned by A, order by A. This is a window function. And this was also crashing the server. When running SQLreduce on that query, it does not reduce much. It discovers that it can replace this A by a null, which is in my metric more simple than the A. And it discovers that the partition by is redundant and it just needs the order by here. But it's basically the same query as before. But when manually reducing that query, Tom Lane, one of the leading Postgres developers back then, actually figured out that the query could be rewritten, that the order by is basically pulled up to the top and pushed down there. So this is arguably more simple than that one, but we can again apply SQLreduce on that one, and there's actually room for improvement there. Does anyone see where it is? It's quite simple. We can remove the A. So when running SQLreduce on that one, it still beats Tom Lane by whatever. Okay, right. So I hope this will be useful in tracking down the more nasty crashes that sometimes are happening, and yeah, it was fun writing it. Thank you.
Thank you, Christoph. Are there any questions?
Perhaps a silly question in this context. Can you also use it to reduce perfectly fine SQL statements and make them shorter so that people will read them better? So with the same functionality, but then
it
shorter.
does not preserve functionality. It's if you give it a perfectly working query, it will just reduce it to select, because it's the same result. So we're not checking the result. We are looking for crashes anyway, so there is no result anyway. You might think about applying the same for queries that produce answers, but then you would probably have to do much more complex operations, because the operations I'm doing are quite blunt.
More questions? Yes.
So if I understood correctly, if you start at one node in the parsing tree, you remove a part and then it still crashes, you continue from that point on.
Yeah.
But if you had started at a different location in your parse tree, it still crashed and you continued from there on, maybe you would have found an example which is even shorter.
Yes, I was thinking about that. So the question is, does the tool find a global minimum or a local one? It does find a local one, but I think in practice it won't make much of a difference, because the tool tries to apply the large reduction steps first, and then only go to finer steps. So it tends to find something that is quite small. And also there's a combinatorial explosion if you explore all paths in that search tree. And I was trying that in the beginning and it didn't go anywhere. And this has actually linear runtime. It tries to reduce each node only once, or only O of one many times. So it's guaranteed to terminate in linear runtime, which is also quite nice.
Okay, we'll wrap that here. Next one is Phil. He's already in line. If you have any further questions, feel free to contact or ask Christoph during the rest of the day. And see you in 5 minutes then.
Thank you.